All right, hello, welcome to CSIT 170. This is Discrete Math. This is our first lecture. It's going to be on section 1.1, which is about propositional logic. So to start off with, a proposition is a declarative sentence that is either going to be true or false. It's making a claim about something about reality. So here's some quick examples of propositions. Number one, the moon is made of green cheese. This is making a claim about the structure of the moon. And this is a false claim. Trenton is the capital of New Jersey. This is making a claim about what's the capital of New Jersey. This is a true statement. This is a true proposition. And finally, 1 plus 0 is equal to 1. This is making a mathematical claim, but it's still a statement, still a declarative statement, and it still counts as a proposition. And in this case, it's also true. Okay, so these are all propositions. Then you've got non-propositions. These are all sentences or questions or statements that are not making a claim about reality. So first of all, sit down. This is a command that doesn't have a truth value. It's not true or false. What time is it? This is asking a question. It's not making a claim. So it can't be a true or false question. And then you've got something like x plus 1 is equal to 2. Now, this is technically making a claim, but we don't know what x is, so we cannot determine the truth value of this statement, right? So if x is 0, this is a false statement. If x is 1, this is a true statement. Because it's not specified what x is, it cannot be determined, right? So this is not going to be considered a proposition. Now in algebra or math, when you see something like this, you'll solve for x in order to force this equation to be true, but that's built on an assumption that we have to make that statement true. In this case, it's not inherently true or false as it's given. Okay, so what are we going to do with propositions? Well, we've got something called propositional logic. It's a system of logic that we're going to build up from propositions. And we can denote propositions. We don't have to write them out all the time. We can use letters or variables, as we call them, like P, Q, R, S, so on and so forth. We can define a proposition this way, and then it's going to give us a bit of a shorthand for working with it. So a proposition that is true is going to be denoted by a capital T. Proposition that is false is going to be denoted by a capital F, and this is going to tell us the truth values right away. All right, so then we can go ahead and we can use what are called connectives to construct compound propositions. So we're going to make combinations between these individual propositions, and we're going to be able to make more complicated claims or arguments and things like that from these propositions. So what do these connectives look like? So we've got a little table here. This is the name of the connective. This is the symbol that we're going to use to denote it, and this is essentially what it means in everyday language. So first of all, we've got the negation. It's going to be denoted by this little mark here, and it just means not. So if I have a negation in front of, say, a proposition called P, this just means not P. Then I've got the conjunction. It has this little caret symbol. This just means and. So if I have that between two propositions, like P and Q, this is just going to mean P and Q. Then we've got the disjunction. It looks like a little V. This means or. So written like this is going to mean P or Q. Now this is, we should specify, this is the inclusive or. So that means, we're going to talk about this more in depth, but this means either P or Q or both can be true. Then you've got the exclusive or. So this has got that little circle with like a plus sign in it. This also means or, but this is going to mean just one or the other, not both. Then you've got the conditional. This is a very important one, and this is going to be denoted by an arrow, and this is usually read as something like if P, then Q. And then finally, you've got the biconditional, which is an arrow with arrowheads on both sides, and it's going to be read as if and only if. So let's dive into each one in depth and see what this looks like. So let's start with the negation, not. What we've got here is called a truth table. Okay, so this is our truth table. And what we do is we list out every possibility for our propositions. So we're only dealing with the one proposition here, it's P. And in the case that P is true, well then not P, whatever the opposite of P is going to be false. In the case that P is false to start off with, well then the opposite of P should be true. Okay? And that's exactly what we've written here. So when P is true, not P is false, or the negation P is false. When P is false, the negation P is true. So if we're talking about an example here, let P mean the earth is round. This is a true statement to start off with. And if we put the negation in front of P, this is just going to be interpreted as the earth is not round. Okay, that's a false statement, just like we have here. So if we started off with a true statement, we negated it, now it's a false statement. You can also look at this, if you kind of want to just think of this negation as something that we're tacking on to the beginning of the sentence, you can kind of read it as, it is not the case that the earth is round. And in some cases, this way of reading a proposition is a little bit easier. Okay, so that's a negation. It's pretty straightforward. Next, we've got the conjunction, which is and. So here's the truth table for and. Now this one's going to involve two propositions to start off with, unlike negation, which only needs one. So for and, we're going to have P in our first column, we're going to have Q in our second column, and we're going to go through every combination of possibilities. So to start off with, the first row is the case where P is true and Q is true. And in this case, the statement P and Q is also true. And in fact, this is the only case where P and Q is true. It requires both elements, both propositions, to be individually true. Okay, we're going to see an example in a second. And in all of these other cases, when P is true but Q is false, P and Q is false. If P is false but Q is true, again, the combination of them is false. And if they're both false to start off with, then certainly P and Q is going to be false. So what does an example look like? You might define P as the statement, I am at home. Q as, it is raining. Okay, so their conjunction is going to simply be, I am at home and it is raining. So if you think about this in context of the truth table, this is only a true statement if you're both at home and it's raining outside. Right? If you're not at home but it's raining, this is still a false statement. If you are at home but it's not raining, it's a false statement. And if you're neither home nor is it raining, then certainly it's a false statement. That will be our last case here. Okay? So this is only a true statement if both elements are true simultaneously. That's the conjunction. Then we've got the disjunction, which is going to be known as the inclusive or. And here's our truth table. So the inclusive or is a lot more forgiving. This one's going to be true as long as just one of these statements is true. So if they're both true, then certainly the whole thing is true. If just the first one's true but the second one's false, the whole thing's still true. If the first one's false but the second one's true, the whole thing's true. So it's only ever going to be false if neither P nor Q are true. Okay, so when they're both individually false. That's the only time P or Q, the inclusive or the disjunction, is going to be false. So let's take a look at an example real quick. We've got P, I am at home, Q, it is raining. Same example from before. So if we put them together, the statement comes out to, I am at home or it is raining. So this is fine if you're home, but it's not raining. This is still a true statement. It's also fine if you're not home, but it's raining. Also still a true statement. It's fine if you're both home and it's raining. Still a true statement because you're just making the claim of or. The only time it's going to be false is if you're not home and say it's sunny outside. Okay, so in this case for the disjunction, only one or the other needs to be true in order for the entire statement to hold. And it's only going to be a false statement if both elements are false simultaneously. So that was the inclusive or. Let's take a look at the exclusive or now. So this one has that different symbol, the plus sign, and that circle. This is only going to be true if exactly one of the propositions is true. So this is kind of making a claim about one or the other, but not both. We cannot have both, so both cannot be true at the same time. It's either P or it's Q. And of course, if it's neither of them, then it's still a false statement. Okay, so let's see what an example looks like. Say you go to a restaurant, you want to order something, and you've got propositions like this. So P could be something like soup comes with this entree. Q would be something like salad comes with this entree. So they might offer you these choices in the following statements. Soup or salad comes with this entree. You're going to pick one or the other. You're not going to get both as a side. Okay, so you don't expect to get both, but one or the other. And that's the idea behind exclusive or. Next, you've got the conditional, which is an important one. This one's going to get a little bit more involved. And this is really just going to translate to if, then. So in terms of P and Q, we're going to read this as if P, then Q. So let's look at this truth table here to start off with. If P is true and Q is true, then the whole statement is true. That makes sense. If P is true but Q is false, the statement is considered false. It didn't hold up because we said if P, then Q. If P is true, then Q should be true. But if it's not, well, then that statement doesn't hold up. And then we've got these two interesting cases here where if P is false, regardless of whether Q is true or not, the statement is considered true. And we're going to come back to those two cases in a second. But for now, we're just going to need to know that the conditional is only false if the antecedent, so that's the name for P, the thing that comes before the arrow, the proposition that comes before the arrow, if the antecedent is true and the consequent, the letter, the proposition that comes after the arrow, Q in this case, is false. So if the antecedent is true and the consequent is false, that's the only time the conditional breaks down. Okay, so let's look at some examples. P is, it is raining. Q is, the ground is wet. So naturally, if I put that together in the conditional format, if it is raining, then the ground is wet. If it is raining is our antecedent, the ground is wet is our consequent. Okay? So no. In reality, there doesn't need to be some actual connection between the antecedent and consequent. In this case, there is raining and the ground being wet. But the truth value of if P then Q, or the conditional, really just depends on the truth values of P and Q as per the table. Okay, so let's look at some examples. Okay, so these implications are fine logically, but they don't convey much knowledge. So here are two examples. The first one says, if 1 plus 1 equals 3, which it doesn't, it's false, then Isaac Newton is the president, which is also false. And yet, this entire statement, if you go back to our table, has a truth value of true. So this is actually a true statement. Okay, hold on to that thought for a second. We've got another example. If the moon is made of cheese, then I'm richer than Bill Gates. The moon is not made of cheese, and I'm not richer than Bill Gates. So again, we've got false and false, but this entire statement is true. So these are going to be called vacuously true statements. Both of these statements have a true truth value because in both cases the antecedent is false. So these are nothing more than hypotheticals, right? This is in some hypothetical universe where 1 + 1 is equal to 3, then Isaac Newton would be the president. In some hypothetical universe, if the moon were made of cheese, then I'd be richer than Bill Gates. Okay? So we just assign these to have a truth value because it's actually going to be very convenient to use, and it makes our system of logic complete and consistent. So that's really why this was done, but otherwise, these don't really convey any important information. These are just hypotheticals. They cannot be tested or investigated. They're just put as true by default. Okay? And we're going to see later on in the course why this was done, why that makes sense, almost mathematically, actually. All right? So now you have a couple of different ways of expressing this if P then Q, or this conditional, how we can read it. And these are different ways you might see it written. Of course, you've got if P then Q, that's our basic starting one. You've got this one, which is a little more complicated, Q unless not P. This is going to make a little bit more sense when we talk about necessary and sufficient, but this is a little bit more complicated way of thinking about the same thing, but it implies the same conditional statement or implication. You've got Q if P. All I did here was just reverse the order, but it's saying the same thing. You have Q if you have P. If P, then Q. Q whenever P. Q follows from P. P implies Q. And then you've got some important ones. P only if Q. This is also going to make a lot more sense when we talk about what we're going to talk about next, which is necessary and sufficient. So essentially what we're saying is P is only going to happen if Q happens, which is interesting because it seems like we're going backwards. P is sufficient for Q, whereas Q is necessary for P. So let's look at this. Why does that make sense? What are sufficient and necessary talking about? Let's suppose we have two propositions. P, there is fire. Q, there is oxygen. So if we have the statement, if P then Q, this is going to translate literally to, if there's fire, then there's oxygen. Now, what we're saying here, P is the sufficient case or condition for Q. So fire is sufficient for oxygen, and Q is necessary for P. So oxygen is necessary for fire. Okay, and that makes sense. Oxygen is necessary for fire to exist. You cannot have fire without oxygen. On the other hand, fire is sufficient proof that oxygen is present. Having fire guarantees that oxygen is present. Again, because fire cannot exist without oxygen. So if there's fire, there must be oxygen here. Okay? So we can deduce the presence of oxygen from the presence of fire because of this relationship, that oxygen is necessary for fire. All right? So that's necessary and sufficient. And we'll look at an example of that later as well. Now let's talk about converse, inverse, and contrapositive. So from if P then Q, we can form new conditional statements if we kind of play around with the order or negation. Okay, so let's look at, first of all, our original statement. If P then Q. And I can say P is raining, Q is that the ground is wet. So if it's raining, the ground is wet. Simple, straightforward. Now I could have the converse. So what I'm doing is I'm swapping the order of those two. Q is going to become the antecedent, P is going to become the consequent. And now the statement is going to read as, if the ground is wet, then it's raining. Okay, that's a different statement than if it's raining, the ground is wet. The inverse, we keep the original order. P is here, Q is here, but then we put a negation in front of each one. So now the statement reads, if it's not raining, then the ground is not wet. And finally, we've got what's called the contrapositive, where we apply both operations. So we're going to do the switching first, and then we're going to apply the negation on top of that. And this statement is going to read as, if not Q, then not P. If the ground is not wet, then it is not raining. Okay. Let's look at an example and see if we can find the converse, inverse, and contrapositive of the following statement, and we can determine each of their truth values. Let's see how this looks. Okay, so we've got the original statement. If you are human, then you are mortal. Right? You're going to die. Your life is temporary. That's the idea. Okay, so here, human, this is our, say, P to start off with. This is our original antecedent. Mortality is Q. That's our consequent to begin with. Okay, so I've got them in blue and red here. Then if we're looking at the converse, well, we know that the converse involves flipping these two. So this one is going to have to come first. This one's going to have to go afterwards. So this one should read, if you are mortal, then you are human. Okay, so first of all, the original has a true truth value. Human life is indeed temporary, at the moment at least. So this is a true statement. If we flip this, if we make it, if you are mortal, then you are human. This is the converse. Is this a true statement? No, not anymore, right? You don't have to be a human to be mortal, right? If you're mortal, you can also be an animal, right? Or an alien potentially, or something like that, right? So it is false that mortality implies humanity. Okay, that's the converse. Now let's think about the inverse. Remember the inverse, we're going to keep the original ordering. We're just going to put a negation in front of each part. So this one should read, if you are not human, then you are not mortal. Right? If you are not human, then you are not mortal. So we kept the same ordering as the original. We're just throwing a not in there, a negation in front of each condition. And again, this is also going to be a false statement. Okay? You don't need to be human to be mortal. So if you're not human, you can still be mortal. Animals have temporary lives too. Okay, and finally, we're going to look at the contrapositive. And the contrapositive is switch the order and throw a negation in front of both. Okay, so this is going to look like we're going to put the mortal condition first, the human condition second, and we're going to put the nots in front of each one. In other words, you can think of the contrapositive as the converse, the swapping of the inverse. Okay, so when we put both operations together, we get what's called the contrapositive. So if you are not human, so this one's coming here now, then, if you are not mortal, then you are not human. Okay, so contrapositive is, if you are not mortal, then you are not human. This statement is actually true. If you're not mortal, then you're not human. You're some other kind of being, right? Some sort of immortal alien or god or some mythological creature or something like that, right? You're not human. So the contrapositive actually shares the truth value with the original statement. The inverse and the converse are going to have the opposite truth value. So if your original statement were true, these two will be false, your contrapositive will be true. If your original statement was false, these two are going to be true. and your contrapositive is also going to be false. All right, so one quick note I want to make. If we're going to relate this example to necessary and sufficient conditions, we can say that mortality, at least in the given original conditional statement, is the necessary condition for humanity, right? So you cannot be human without being mortal. And then humanity, so being a human, is a sufficient condition for mortality. So if you are human, that's sufficient enough evidence or information for us to conclude that you will be mortal. Okay? So that's with that example. Now, last thing I want to talk about is the biconditional, which is known as if and only if. Okay, so let's look at how this works. So here we've got the truth table, we've got P, Q, and then P if and only if Q. Okay, so if both are true individually, the biconditional statement will be true. If either one is false, then the biconditional statement will be false. And now if both are false, the biconditional statement will be true. So in this case, what we really can conclude is that both elements, or both propositions, P and Q, have to have the same truth value in order for the biconditional to be true. Okay. So if we think of a conditional statement as a one-way street, then a biconditional is like a two-way street. So it's going both ways. And let's see how this looks. Okay. In other words, the conditional relationship that we're used to, so if P then Q, right, or if then, this is going to hold both ways, actually, in a biconditional statement. So it holds in the P to Q direction, if P then Q. It also holds in the other opposite direction, right? So if Q then P. So this is the case where both a statement and its converse are true. That's what gives us the biconditional statement. Okay, so let's see what an example like this looks like. Let's suppose P is the statement, I get a good grade. Q is the statement, I study hard. So how does this look? So if we have the if P then Q, we can write this as, if I get a good grade, then I study hard. Okay, that's nothing new. That's just our conditional at work. Getting a good grade here is a sufficient condition. Studying hard is the necessary condition. Now, written a little bit differently, and this is going to be more in the language of the if and only if that we see in the biconditional, you could say, I get a good grade only if I study hard. The reason being, studying hard is necessary for getting a good grade, right? It's just like saying that if there's fire, there's oxygen. In other words, you could say, there's fire only if there's oxygen, right? We cannot have fire without oxygen, oxygen being its necessary condition. It's the same thing as holding here. Okay, so this only if is referring to the necessary condition, which is the consequent. Okay, now if we go the other way, we can flip this around, and this is now going to say, if I study hard, then I get a good grade. Okay, so far so good. We can rewrite this and say, right, this is one of those switching of the order, but it means exactly the same thing. I get a good grade if I study hard. Okay, so all that's doing is that's just putting this here. And this is not even a converse or anything. Right? We're just taking the same language and we're just putting it in a different order. That's all we're doing. Okay, so if I study hard, I get a good grade. I get a good grade if I study hard. It's the same statement. Okay, but this is going to help illustrate where the if and only if is coming from. Okay, so if this is true and this is true, then we've got this if and only if, and we can put it together and we can say, I get a good grade if and only if I study hard. So this if refers to this if Q then P direction. Only if is referring to the if P then Q direction. Okay, so that's our final connective, the biconditional. Okay, so this is our introduction to propositional logic. We'll pick up from here next time with compound truth tables, and we'll see how the truth tables that we started with these initial connectives are going to get more and more complicated when we compound them together.